All right, good morning everybody and welcome to the second day of the MATLAB Expo 2021. How's everybody doing today? You awake and excited? Are you ready? All right, kind of a quiet audience, but I understand it's still a little bit early. I want to start by thanking the MathWorks for inviting me to speak today. I'm super excited about being here, and I want to thank everybody at home who's watching on their computer and participating in this expo virtually. And then, of course, I want to thank all of you in the audience who's here with me today. Right, this is a virtual conference. I don't actually need to be here. All right, I've got an idea. Could somebody please just sort of dim the lights a little bit? Maybe just a little bit more? Perfect. Virtual me. Yes, that's much better. Hi everyone, I'm Brian and I'm an engineer.
Hi, Brian.
I started out as a spacecraft guidance, navigation, and controls engineer at Boeing, and then at Planetary Resources before ultimately settling into more of a systems engineering role. And then about 3 years ago, I started my own company, Engineering Media, where I tend to focus more on general engineering education. And in this role, I get to work on some really fun things, like creating the map of control theory. And then more recently, I've been working on an educational resource site called resourcium.org. But I'm probably best known as that guy on YouTube who teaches control theory. My YouTube channel is Control System Lectures, and over the last 9 years, it has grown to over 220,000 subscribers with 17 million views across all of my videos. Now, I haven't been making videos for this channel lately because a few years ago, MathWorks graciously invited me to help contribute to their MATLAB Tech Talk video library. And I'm happy to say that so far, we've been able to add over 60 videos to the collection that cover all sorts of interesting topics, like systems engineering, autonomous navigation, robust control, sensor fusion and tracking, reinforcement learning, and more. And the idea of these videos is to introduce the topic and then provide a foundation from which you can build a more solid understanding. Creating one of these Tech Talk videos takes 2 weeks from start to finish. The first week is dedicated to, just understanding the topic in general and trying to craft a working script. And then the second week is for animation and reviewing with the technical experts at MathWorks and final editing. And this was definitely a relaxed schedule when I was covering topics that I'm an expert in, but increasingly, the stories I'm trying to tell are ones that I have very little experience with. And so I often find myself having to learn a new topic as quickly as possible that is outside of my discipline so that I can turn around and create a useful and coherent story. I think in a way this is something we all experience, where we have to quickly learn something outside of our discipline, regardless of whether you're trying to tell a story, or develop a product, or do some kind of research. So I thought I would take some of my experience and talk about 2 things. The first is I want to briefly cover why I think interdisciplinary knowledge is so important, both for the project team as a whole and for each individual person on the team. And then, understanding that we need interdisciplinary knowledge, I want to walk through how I approach learning new things for my videos and what level of understanding I try to get to. And specifically for this audience, I want to touch on how MATLAB, Simulink, and MathWorks in general play an important role in all of this. All right, let's get going. Why do we need interdisciplinary knowledge? Let's start by assuming this hypothesis is true. Technology is becoming more interdisciplinary, and therefore, we as engineers and scientists need to have more interdisciplinary knowledge. And by this, I mean that on average, if you look at an engineered product, the number of unique skills and bits of knowledge that is needed to design, manufacture, build, test, distribute, market, and maintain that product is increasing over time. And I think we all generally have a feeling that this is true, but it turns out that this has been researched and proven. Well, part of it has anyway. I couldn't find much research on diversity in product development and the products themselves, but there are at least 2 papers that looked at how research in science and engineering cite more diverse resources today than they did 40 years ago. So we might claim that with our research becoming more interdisciplinary, that it makes sense that the things that we can engineer can draw from that greater diversity and therefore require teams producing those products to have more diverse knowledge. This increase in product diversity is, in part, a consequence of the age of digital transformation. Digital transformation is basically where we try to pack in as much digital technology into everything that we do, whether that's a product or a service or just how we run our businesses. Now, we're not just doing this because we can. Well, not always anyway. In many cases, it makes the product better, even at the expense of requiring more interdisciplinary knowledge. Now, as an anecdotal example, take the dishwasher. It was first patented in 1850, and it started simply as this wooden box with this sort of flappy paddle wheel that you could turn by hand to gently splash water on the dishes and scrubbers. To design something like this, you need to understand woodworking and have a basic understanding of building reliable, rotating mechanisms. And then in 1893, the dishwasher advanced to using water pressure to blast the dishes clean rather than relying on scrubbers. It had a copper boiler to heat the water and then pumps to create the needed water pressure. And to build this version, the inventor, Josephine Cochrane, needed to have some understanding of metals and heat transfer and water pumps, in addition to the woodworking and rotating mechanisms. And then from there, we added drying capabilities and sensors and digital interfaces and on and on and on. And we now have a dishwasher with increased capabilities and better reliability, better efficiency, and maybe it's also cheaper to manufacture. And all of this makes the dishwasher more valuable. It improves the user experience, and so it's beneficial to add all of this stuff. But it requires a team that has a lot of knowledge. It takes understanding circuit design and power distribution and control theory and software engineering and efficient manufacturing and more. Plus, new technology is constantly being added. In fact, I just bought a new dishwasher a month ago, and it can connect via Wi-Fi to my smart device. And with just a few button pushes, it allows me to change the order that the detergent is dispensed. I mean, it's really quite impressive.
I'm sorry, Dave. I'm afraid I can't do that.
What was that? Oh, for the last time, dishwasher, my name is Brian. It's Brian. Building sentience into it might have been a step too far. Okay, where was I? Oh, right. These advancements improve user experience. Well, at the very least, they differentiate a company's product from its competitors. And companies want their products to stand apart, to be cheaper, to be more reliable, and to do more things. And all of the stuff that falls under the umbrella term of innovation. And to me, being innovative means making use of existing knowledge and technology to accomplish something new. And because of the continuous advancements in science and engineering, the existing knowledge and technology base that we can pull from is always growing. So we have the ability to be more interdisciplinary by adding things like Wi-Fi and machine learning into products that wouldn't have been possible a decade or so ago. So, why do we need interdisciplinary knowledge? Well, it's to keep up with the ever-growing knowledge and technology base so we can continue to be innovative. All right, that covers the first part. We're just moving right along here. And to transition us to the second part of this talk, I want to present to you, with absolutely no context, a video that I've titled Me Shaking a Breadboard. All right, let's give this a shot. We've got left and right, not registering anything, forwards and backwards, up and down. All right, let's give a high five a shot. Oh my gosh, that's awesome. I can't believe that worked. Did you figure out what's going on there? Yeah, That's a super cool high five counter that I recently built for the MATLAB Tech Talk series on deep learning. And for this project, I use acceleration data from a sensor that is mounted to the breadboard that I'm holding to count the number of times I make a high five motion. This was something I'd wanted to build for a while, but I wasn't exactly sure how to go about it. And then when I was making the deep learning series, I thought maybe this is a good opportunity to see if deep learning is a practical solution for my problem. I feel that this is a similar situation that a lot of companies find themselves in. They want to assess whether a particular bit of technology is right for their product, but they currently don't have the expertise in-house to make that determination. And rather than always go out and hire in a new skill set, they ask their existing workforce to absorb this request. And so they have to get up to speed quickly. Similarly, going into this project, I knew nothing about deep learning, which I'll be honest is not ideal if your goal is to teach it. But even still, I was able to go from initial ignorance to getting this proof of concept working in just a few days. Now, a lot of credit for my quick success goes to the fact that I could just buy a cheap sensor and microprocessor, and that I could use the existing deep learning functions and applications in MATLAB without having to write my own. And I could start from an example that demonstrated how to use deep learning to solve a problem that was very similar to mine. And I was able to talk to the experts at MathWorks who corrected my misunderstandings along the way. But that's one of the points that I want to make in this talk. When I'm faced with having to create something fast that is outside of my discipline, then it's really important for me that I leverage the expertise and knowledge of as many people and as many existing things as I can. But the other point that I want to make here is that I don't want to give you the impression that I just snapped together some hardware and ran some functions in MATLAB without having some level of understanding of what it all does. In my experience, it's almost never a good idea to add technology into your project that you don't understand, because it's hard to have confidence that it's doing the right thing. So with that in mind, let me walk you through portions of my process for developing this knowledge. And keep in mind that how you learn is personal, so what works for me won't be a universal solution. But hopefully some of it will be useful. Or at the very least entertaining, so that you can walk away from this thinking that, well, I didn't learn anything, but at least I didn't fall asleep. And I guess speaking of falling asleep, are you still awake out there? Why don't we take a brief intermission and give everyone a chance to stand and stretch and wake up a little bit before we continue. All right? See you in a little bit. And welcome back. All right, when I'm first venturing into a new discipline, it's really daunting because there is always so much information out there, and I know nothing. So where do I even start so that I'm not just wasting a huge amount of time? And there are three main things that have helped me navigate through this morass. One is to start by broadly taking in as much about the entire field as I can. Two, it's to find examples that are similar to what I'm trying to do and modify them to develop some intuition. And three, it's to reach out to the experts to keep me on the right path. And to sort of put all of that into context, let me show you what that looked like on my high five project. In this first phase, I'm just trying to consume as much information about deep learning as I can. But to be clear, I'm learning next to nothing in this first phase. I read something and I move on. I don't try to understand it. I don't try to implement it or practice it. Nothing. I'm just reading concepts and storing it away as a thing. And the goal after the end of this first phase is to hopefully walk away with sort of a map of deep learning, showing all of the major areas within this field. Something kind of similar to my map of control theory. I think it's helpful to look at something like this and realize that if I was going to develop a control system and didn't know where to start, at least I know that I need to consider things like how to model and simulate my system. I have to think about what I want my system to do, and how I will estimate state, and how I will control it, and how I will analyze the system along the way. And if I didn't know much about control engineering and I just Googled it, I think I would be under the impression that focusing on the control method, like PID, is the most important thing. and I should spend a lot of time learning that. And it wouldn't be until much later that I realized that modeling and simulation is probably where I really want to focus my efforts early on. And so in this mapping phase, I try to keep everything at sort of equal importance until I know enough to start to dive in deeper. And similarly, I didn't know much about deep learning, and when I Googled it, I got the impression that understanding the different types of deep neural network architectures and the fundamentals of the training algorithms are where I should spend most of my time. But it turned out, for my project, that wasn't going to be true at all. So instead of trying to pick a very specific area and then diving into learning it in detail, I'm just collecting concepts here and forming a mental image of the bigger picture. And with this global picture slowly coming into focus, I then try to reframe my problem to fit within the scope of the map, so that I can start to figure out the areas where I think I need additional depth. I'm looking to classify high fives in acceleration data. This is time series data. And so even though I know that there's a bunch of cool stuff that's happening with image recognition and natural language processing, I can probably avoid most of that for now and dive a little deeper into time series deep learning. Often, I'll focus on working through examples and changing parameters and variables and algorithms to build some intuition into how they affect the result before I try to dive into the mathematics. I always found that reading the technical papers with their specific jargon is so much easier if I have an expectation of what the math is doing. And for my project, I stumbled across a web page on the MathWorks site that I wish I knew about earlier. Under Support and Examples, and then if I scroll to the category of Deep Learning Toolbox, I can get a list of all of the deep learning examples for MATLAB and Simulink. And there are hundreds of them. I couldn't believe it. And right at the very top, there was time series forecasting using deep learning. So I thought I would check it out and see what I could learn. This example uses a long short-term memory network to forecast the number of chickenpox cases that will occur, given the number of cases in the previous month. And I wasn't sure how this was going to relate to high fives, but I needed to start somewhere. So I ran this example and then spent some time trying to figure out exactly what it's doing. And part of that process is to adjust some of the parameters to see how it affects the end result. The idea here is that I can start to build up some intuition by playing around with these examples. And at this point, I'm starting to feel pretty good. I mean, I successfully ran an example and I'm learning a lot about how it works. But the deeper I go into topics, the more I run the risk of spending way too much time on the wrong thing. And it turned out this wasn't the best example for me because I'm not trying to forecast into the future, I'm trying to label an existing pattern. So I turn to the experts to correct my path. I reach out to someone who knows what they're doing before I get too far down any particular path. But, and this is important, it's after I've learned enough that I can have an intelligent conversation. If I reach out too early in this process, I find that I don't understand the landscape of the field well enough and can't describe my problem well enough within that landscape to really get much from their advice, and I end up just wasting both of our time. For my project, I talked to the application engineers at MathWorks and then learned that I should probably focus less on developing a network myself and just start from a pre-trained network with transfer learning. They pointed me to a better example to follow that walked through transfer learning using time series data. And this was the example where I spent the most time developing my understanding. I found out that I could pre-process my time acceleration data into an image with a scalegram, and then feed that image into a network like GoogleNet or SqueezeNet that is trained to recognize features in images. And then by swapping out a few of the last layers in the network, I could retrain it to recognize high five patterns in these scalograms. And this was great because I had never heard of scalograms before, and I didn't think about converting my time data into an image and then using an image network to classify it. And so this gave me concrete direction to go off and study other resources where I could learn the details of the scalegram and what a pre-trained network is providing and how to modify them for transfer learning. And I find that once I have that direction, finding those other resources across the internet becomes so much easier, because now I'm not just Googling how to deep learn, but I can focus my search on the things that are actually beneficial for my project. I can search for scalegram and find helpful videos and documents and blog posts that allow me to dive even deeper into these topics and learn a bit more so that I can start applying it to my problem. And then the loop starts again. After some amount of time, I reach out to the experts to course correct, figure out where I should be focusing my time, finding those resources, and then learning more. And I loop back again and again until, well, usually until I just run out of time. Often I find it difficult to know when to stop marching up this knowledge spectrum because more knowledge is almost always beneficial, so it's easy to keep going. Luckily, deadlines know when to stop. And so, as long as I have time, I continue refining my skills and trying to make the best decision possible. Or, in my case, tell the best animated educational story until my 2 weeks is up. Alright, so that's my approach. When I'm learning something new, I start very broadly, treat everything as equal importance without diving deep into any particular topic. And then I use examples to build some intuition and figure out where to add depth and reach out to experts to correct my misunderstandings before I go too far down the wrong path. And hopefully you find this useful or some other method that works for you, because as we talked about, with our products and research becoming more interdisciplinary over time, I think most of us will be constantly faced with having to learn new theory and technology and commercial widgets, and we're going to have to learn them quickly, at least to a level to be able to perform trade studies or get a working prototype to determine if that bit of technology is worth spending additional resources on. All right, so that's where I'm going to leave this talk. Thank you for watching and for sticking around until the end. You made it! And if you're interested in anything I mentioned in this talk, the links to everything are provided in the PDF that accompanies this presentation. Specifically, if you want to see the video where I build the high five counter, or any of the other MATLAB Tech Talks on all of those different topics, definitely check out the links in the document. All right, thanks again everyone for watching. I hope you enjoy the rest of the conference. Take care. You hear that, Dishwasher? We made it to the end of the presentation. High five!
I'm sorry, Dave. I'm afraid I can't do that.
Oh, come on, you've got to be kidding me. You had one job. Well, I guess to be fair, it was to wash dishes, and you do that pretty well, so I'll forgive you.
I'm sorry, Dave. I'm afraid I can't do that.
Yeah, you said that already.